I know what you're thinking. That's all well and good. This digraph stuff seems interesting, but why are you doing it in a linear algebra course? And the idea is that directed graphs are nice for humans to look at because they represent something visual, and humans like to think visually. Computers, on the other hand, don't think visually. Computers think numerically. So the idea now is how could we get a computer to work with a directed graph? And the idea starts with this notion of the incidence matrix of a directed graph. So what is the incidence matrix of a directed graph? Well, the incidence matrix encodes all of the important information in the directed graph. So here what we're looking at is an example where we have a directed graph that has 5 nodes and it looks like we have 6 arrows. So what the incidence matrix is a matrix where the number of rows is the same thing as the number of nodes in the directed graph. So here, because this directed graph has 5 nodes, the incidence matrix will have 5 rows. The incidence matrix has number of columns equal to the number of arrows in the directed graph. Here the number of arrows is 6, so this incidence matrix has 6 columns. Now I want to point out the rows and the columns have meaning numerically to the nodes and the arrows. So I've included labels for each of the rows according to the nodes and labels for the columns according to each of the arrows. Those labels are not part of the matrix. Those labels are just there for me to remind myself which column corresponds to which arrow and which row corresponds to which node. So how do we build the incidence matrix? Why is this matrix filled with all these zeros and ones and negative ones? Let's focus on the first column of the incidence matrix. The idea is that this first column corresponds to the first arrow in the directed graph. And the first arrow in the directed graph points from V1 to V2. So this arrow points from V1 to V2, and none of the other nodes are relevant as far as the first arrow is concerned. So the way we numerically encode this in the incidence matrix is we put a -1 in the first row because that corresponds to the first node, and that's where the arrow starts. Then we put a 1 in the second position because that second position corresponds to the second node, and that's where the arrow points to. Since every other node is ignored by A1, we put zeros in those positions. So we focus on an arrow, we look where it starts, that position gets a -1. Then we look where the arrow points to, that position gets a 1, every other position gets a 0. Great, so that's the first column of the incidence matrix. Let's look at the next column. The next column is the second column, which corresponds to the second arrow in the directed graph. This arrow points from V2 to V1. So we're going to put a -1 in the second position to indicate that this second arrow starts at V2. Then we put a 1 in the first position to indicate that this arrow points at the first node. All of the other positions get a 0. Let's look at the third column. The third column corresponds to the arrow A3. A3 starts at V3 and points at V4. So we get a -1 in the third position and a 1 in the fourth position, and every other position gets a 0. If we look at the fourth column, this one corresponds to A4, and the fourth arrow starts and terminates at the same positions that A3 does. So this column is actually the same as the previous column. We get a -1 in the third position, a 1 in the fourth position, and zeros everywhere else. The fifth column here corresponds to the fifth arrow in the directed graph. This one starts at V3 and points at V5. So we get a -1 in the third position and a 1 in the fifth position. Everything else gets a 0. And finally, the sixth column in this incidence matrix corresponds to the sixth arrow in the directed graph. This one starts at V4 and points at V3. So we get a -1 in the fourth position and a 1 in the third position and zeros everywhere else. So this is one way to encode all of the information in the directed graph into a matrix so we can translate the visual aspects of the graph we're looking at into numbers. So the idea here is that each column gives information about an arrow in the directed graph. Again, how did we construct this matrix? The source node for an arrow is tagged with a -1. The target node for an arrow, this is a typo, the target node is tagged with a 1. I'll fix that on the slides. And finally, all of the other nodes get tagged with a 0. So source, meaning where the arrow starts, gets tagged with a -1. Target, meaning where the arrow terminates, gets tagged not with a -1, but with a +1. And all of the other nodes get a 0. And the idea here is that directed graphs can be reconstructed from the data inside of its incidence matrix. So let's say that we are working with a directed graph called G, and its incidence matrix is this 3x4 matrix. Let's see if we can't take this incidence matrix and reconstruct what the directed graph looks like. The first thing that I notice is that this incidence matrix has 3 rows, which means that whatever the digraph looks like, it should have 3 nodes. The next thing we can do is we can start to look column by column to see how the arrows fit into the picture. The first column of the incidence matrix has a -1 in the first position, a 1 in the second position, and a 0 in the third position. This is telling us that the first arrow points from V1 to V2. So the first arrow looks like this. The second column has a -1 in the first position and a 1 in the third position with a 0 in the second position. This is telling us that the second arrow points from V1 to V3. So V1 to V3 here. The third column has a -1 in the second position and a 1 in the third position. This is telling us that the third arrow points from V2 to V3. And finally, the fourth column has a -1 in the second position and a 1 in the first position, which tells us that this arrow, A4, points from V2 to V1. And that completes the construction of the directed graph. We started with the incidence matrix and rebuilt the directed graph from that data. So, the constructions go both ways. If you give me the graph, I can give you the incidence matrix. If you give me the incidence matrix, I can redraw the graph. And the idea here is, I mean, this is a beautiful sort of setup here. The idea is that humans like pictures that look like the graph on the right, but computers like data that looks like the matrix on the left. And so now one of the themes of this course is that geometric properties of the directed graph can translate into algebraic properties of the incidence matrix. So let's look at it. Let's say a few things about incidence matrices in general. Remember, a directed graph that has m nodes and n arrows has an incidence matrix that has m rows and n columns. This is what a general incidence matrix looks like. So what's the notation we introduced for this previously? Well, for a matrix that has m rows and n columns, we write A belongs to r to the m times n, or m by n. So the number of columns of an incidence matrix is the same thing as the number of arrows inside of the directed graph. So the next piece of terminology I'd like to introduce is the notion of a weight vector. So weight vectors encode all the data of the weights inside of a weighted digraph. So here we're looking at a figure that's representing a weighted digraph that has 3 nodes and 4 arrows. The idea here is that the first arrow is equipped with the weight -3, the second arrow is equipped with the weight 7, the third arrow is equipped with the weight 14, and the fourth arrow is equipped with the weight 9. So to construct the weight vector, what we do is we initialize a vector that whose number of entries or number of coordinates is the same thing as the number of arrows, and we simply place each weight in its appropriate position. So in the first position of this vector, we're inserting a -3. In the second position of this vector, we insert a 7. In the third position of this vector, we insert a 14. And in the fourth position of this vector, we insert a 9. Again, I'm including A1, A2, A3, A4 here, just so that it's clear which coordinate of the vector corresponds to which position or which arrow in the directed graph. But these are labels that are only for our convenience I don't consider these part of the data of the vector. So this is a vector in R4. This isn't like a 4x2 matrix. So again, that's how the construction works. We got the -3 by looking at the first arrow. We got the 7 by looking at the second arrow. We got the 14 by looking at the third arrow. And we got the 9 by looking at the fourth arrow. And again, this is a vector that lives in R4 because this directed graph has 4 arrows. We can use weight vectors to describe interesting things. So the path vector, by definition of a path, is the associated weight vector. So let's look at an example. Let's say that we transverse a path here. So let's say we start at the node V2 and travel with A3 to get to V3. Then let's say we travel, I misread my own path. So let's say for this path, we have a -1 here. Let's say we start at V3 and travel against A3 to get to V2. Then let's say that we travel from V2 to V1 by traveling with A4. Then let's say we travel from V1 to V2 by traveling with A1. This is a valid path in the directed graph. We traveled against A3, with A4, and then against A1. And so if you look at the weights in this digraph, the weights tell us the path we're taking. The weight on A3 is -1, which indicates that we traveled against A3. The weight on A4 is 1, which indicates that we traveled with A4. And the weight on A1 is 1, which indicates that we traveled with A1. And note that we ignored the arrow A2, so that gets a weight 0. The path vector is the weight vector for this weighted graph. So here, the idea is that we're building the weight vector according to this path. So what is the position in the first the coordinate? Well, that's a 1 because when we took our path, we traveled with A1. The second position is 0 because we ignored the second arrow. The third position gets a -1 because we traveled against the third arrow. And the fourth position is a 1 because in our path we traveled with the fourth arrow. So the language we would use here is we would say that the path vector of the path A3, A4, A1 is the vector 1, 0, -1, 1. Same goes for cycles. So the cycle vector is the vector that organizes the data of a cycle. So let's say that we took a cycle in this digraph. So let's say we traveled from V1 to V3 by traveling with A2. Then let's say that we travel from V3 to V2 by traveling against A3. And then let's say we travel back to V1 by going against A1. That is a valid cycle in the directed graph. And we can organize the data of that cycle into a weight vector. So the cycle vector tells us the path we took. We traveled with A2, so we'll get a +1 in the second position. Then we traveled against A3, so we get a -1 in the third position. And then we traveled against A1, so we get a -1 in the first position. We ignored A4 in this cycle, so we get a 0 attached to A4 here in the fourth position. So the cycle vector here is the vector -1, 1, -1, 0. Okay, so now I'd like to return to this notion of net flow. So we have a beautiful theory that we've now developed. For a directed graph with n arrows, the incidence matrix has n columns, and if that directed graph is a weighted graph, well, we could construct the weight vector, and the weight vector would have n coordinates in it. And each one of these coordinates would give us the weight on the arrow. So I have a little typo here. This should be a sub 2. So we would have the weight for the first arrow, the weight for the second arrow, all the way down to the weight for the last arrow. And here's where the theory gets cool. Remember from our first lecture, what we said is that if we're dealing with an m by n matrix, one way to interpret that matrix as a machine that accepts inputs coming from r to the number of columns and translates those vectors into new vectors that end up in r to the number of rows. So we can view this m by n incidence matrix as a machine that accepts vectors from Rn as inputs and translates those vectors or transforms those vectors into new vectors with m coordinates. And the other thing here that's cool is that the weight vector has exactly n coordinates. So it makes sense here to multiply a by the weight vector and we get some new vector. So it's worth asking, well, what is that new vector? And so the product of the incidence matrix with the weight vector makes sense. Let's look at an example where we calculate that product. So here I have a weighted directed graph. This directed graph has 3 nodes and 4 arrows. So the incidence matrix is 3 by 4. This is a weighted directed graph. So each one of the arrows in this directed graph has a weight, and I can organize those weights in the weight vector. The weight for the first arrow is -3. The weight for the second arrow is 7. The weight for the third arrow is 14. And the weight for the fourth arrow is 9. So my incidence matrix is 3 by 4. My weight vector is in R4. So I can multiply my incidence matrix by my weight vector. And remember, mechanically what this means is that I'm looking at a linear combination of the columns of the incidence matrix, where I use the scalars in the vector I'm multiplying by in the linear combination. So I'll take -3 times this first column, plus 7 times the second column, plus 14 times the third column, plus 9 times the fourth column. And when I do all that arithmetic, I end up with 5, -26, 21. And here's the cool thing about the theory. 5 turns out to be the net flow through the first node. So remember, for net flow, we add all the weights pointing in and we subtract the weights pointing out. So what we would look at if we calculated that net flow by hand is we would take 9 and then we would subtract 7 and also subtract -3. So effectively we would be looking at 9 plus 3 minus 7, which it turns out to equal 5. What about -26 here? Well, that turns out to be the net flow through the second node. So for the second node here, if we calculated net flow, we would take -3 because that's the weight that points in, and then we subtract 9 and 14, and that turns out to be -26. So that's the second coordinate of the output of the incidence matrix multiplied by the weight vector. And finally, 21 turns out to be the net flow through the third node. The net flow through the third node is just 14 plus 7, which is 21. So what we're finding in this example is the theory we've set up is actually useful. If we take our incidence matrix and multiply by the weight vector, we automatically calculate all of the net flows through all of the nodes. So those ugly calculations we were doing by hand earlier can sort of be outsourced to a more elegant calculation, A multiplied by the weight vector. So the matrix vector product calculates net flow. That's the punchline here. So let's state this as a theorem. The incidence matrix A and the weight vector W of a weighted digraph fit into these two statements. A is m by n, so we can view it as a process that transforms vectors in Rn into new vectors in Rm. And the weight vector organizes the weights for all of the arrows, so it is a vector in Rn. Well, when I have a diagram that looks like this, A takes things in Rn and spits as inputs, and then does something with them and spits out a new vector in Rm. That means I can multiply A by this W. And when I multiply A by W, I produce a new vector Rm. In a digraph, m would represent the number of nodes. And the idea is that the ith coordinate of this new vector is the net flow through that corresponding node. So matrix vector products make this problem of calculating net flow much simpler. So you can imagine a situation where you had a directed graph with like thousands of nodes and millions of arrows. If you wanted the net flow between all of those, or through each one of those nodes, you wouldn't want to do those individually. What you would do is you would construct the incidence matrix and then construct the weight vector and multiply them together. And then that gives you a big list of all of the net flows. Pretty cool stuff. This is one of my favorite applications of matrices and vectors because we're talking about problems that involve lots of dimensions But the arithmetic tells us something relevant, or that those dimensions are actually relevant to us. So I think it's a pretty cool theory. That's it for directed graphs for now.